Today I'm going to talk about how to work on SlimWiFi, ultra-low power IoT radio architecture enabled by asymmetric communication. This work is done through the collaboration between the groups from UC San Diego and Baylor University. Ultra-low power communication is one of the hottest research problems in our field, since it can open a wide array of new applications in either consumer IoT or as well as in the industrial IoT. Researchers in our field have published a bunch of papers on backscattering in order to enable the ultra-low power communication. The idea behind is to push nearly every active component to another device, which generates an excitation signal. The IoT device will then backscatter and modulate the excitation signal, and the backscattered signal will be received by another device. Due to the simplified radio architecture, the power consumption can be reduced to at a level of tens of microwatts. But backscatter design relies on the helper device, which introduces a series of problems, such as needing additional custom device, unstable link, in-band or out-band interference, etc. Please refer to this verification paper for more details about these problems. To address this kind of problems, we try to shift our site back to active transmission. We proposed an active but simplified slim radio architecture in order to support standalone operation. But we can still be able to maintain the power consumption at a level of tens of microwatts, similar to what backscatter can do. Comparing to the commercial off-the-shelf radio, the slim radio needs to reduce the power consumption to nearly every component of it. The slim radio first adopts simplified modulation instead of complicated OFDM modulation. For carrier generation, slim radio adopts the open loop generator instead of a closed loop one. And finally, we also reduce the transmit power from 20 dBm to minus 20 dBm. This design enables us to replace the original power-hungry components in the commercial off-the-shelf radios with highly energy-efficient components in the slim radio, which reduce the power consumption by nearly 3 orders of magnitude. However, this kind of low power is not achieved with no cost. These architectural modifications will introduce several challenges, such as incompatible modulation, large frequency offset, and also low signal strength. Due to time restriction, I will mainly focus on the first challenge. Please refer to our paper about how we deal with the last two. The incompatible modulation means that the slim radio cannot generate the complicated waveform like what the commercial off-the-shelf radio does. A quick analogy for this case is like our pad cannot speak the same kind of language as what we can. Therefore, in the IC design society, a typical kind of design will introduce customized radio, acting as a gateway, since they believe that the commercial off-the-shelf radio cannot decode the information from the slim radio. But this will lead to high deployment cost. If you want to make the mobile IoT terminals ultra-low power, you will need to overhaul the entire base station's infrastructures, which may cost billions of dollars. Therefore, we try to answer the question that how can the slim radio directly communicate with the commercial off-the-shelf radio? To answer this question, we introduced a new paradigm called asymmetric communication. Following, we will use Wi-Fi as an example here to explain how we can implement a slim radio that can directly communicate with the commercial off-the-shelf Wi-Fi device. And we will call this kind of slim radio as SlimWiFi. Let me give an analogy for better understanding here. So the communication between the commercial off-the-shelf devices, which is similar to a person talking to another one. The listener will immediately understand what the speaker wants to deliver. In the case of slim radio, the communication is asymmetric. It is similar to that I'm interacting with my pad. The pad has much simpler hardware as what we have and cannot speak the same kind of languages. I usually only know that it is barking instead of they are asking for food. But since we have more powerful brain, we can learn about what are this meaning. Similarly, if we want to enable asymmetric communication between the Slim radio and the commercial off-the-shelf radio, we need to design a method to do similar kinds of conversion. Let's first look into how the commercial off-the-shelf Wi-Fi device processes the waveform. When the commercial off-the-shelf Wi-Fi device receives this waveform, it will first do a series of complicated processing as shown here. The OFDM demodulation procedure it runs in the radio's IC, and therefore it cannot be bypassed or be modified. So with the receiver, we can only get the bit sequence instead of the original waveform. When the input is an OK modulated signal, the device can also provide a sequence. Then the demodulation procedure it is a kind of mapping between the original waveform and the final bits. Intuitively, we can reconstruct the input signal by reverse the whole OFDM processing procedure. Then we can try to extract the information from the reconstructed waveform. But usually, we cannot reconstruct exactly the same kind of waveform as the input is. Since nearly every steps in the complicated OFDM demodulation procedure, they will introduce some problems as listed over here. Yeah, every block, it will introduce a problem. So we propose to solve all these kind of problems by having first a co-design of the transmit waveform and the demodulation, and also have a careful configuration on the receiver side. For the sake of time, I will mainly focusing on explaining one of the hardest challenge over here on the coding area, which is solved through a combination of these two methods. Here shows the FEC decoding and the reverse process. Ideally, we want the reconstructed bits, the x prime, to be similar as the input x. But since the decoding procedure is a -to-1 mapping, but the reconstruction is a 1-to-1 mapping, there will be inevitable errors between x and x prime. So we try to address this kind of problem through two steps based on two observations. The first observation is that there will be fewer coding errors when the receiver is working with a higher coding rate. Therefore, we first trying to configure the receiver working at the highest possible coding rate in order to minimize the number of coding errors. Here gives an example of LDPC coding with the 5/6 coding rate. In the paper, we proved that with the OK modulated signal, after the decoding procedure and the reverse encoding, the error bits will always be located at the parity bits block. This leads to the second observation that the error locations are known a priori and evenly distributed. Then the residual bit errors can be easily fixed by applying convolutional coding to the original bit. So by putting everything or every kind of design mentioned in our paper together, the system will consist of the commercial off-the-shelf Wi-Fi device and the ultra-low power SlimWiFi device. The Wi-Fi device will first run the standard carrier sensing to acquire the channel and reserve access by transmitting the CTS to self frame. Then the Wi-Fi device emulates an OK modulated trigger frame by manipulating the Wi-Fi bit sequence. The SlimWiFi device ultra-low power OK receiver will decode the information and synchronize with the trigger frame. Following the step 2 immediately, the Wi-Fi device will then initiate the demodulation procedure of its receiver chain, and meanwhile, the SlimWiFi device will send an OK modulated signal to the Wi-Fi device. And finally, the Wi-Fi device will decode the OK modulated signal by applying asymmetric demodulation. For the implementation, we use a commercial-off-the-shelf Wi-Fi access point as the host device. There will be no hardware or even firmware modifications needs here. For the SlimWiFi device, we designed a PCB prototype for the end-to-end test and also have an IC taped out to verify the Slim radio architecture. We benchmarked the performance of the Slim radio implementation, and the taped out version power consumption is just around 19 microwatts. For the end-to-end test, we use the prototype version, which contains both ultra-low power transmitter and receiver. We changed the range between the Wi-Fi access point and the SlimWiFi device and measured the goodput. The result shows here that the asymmetric communication is feasible, and the range is a little bit shorter than the theoretical bound we have in the paper due to the imperfect hardware, but the range and bit rate is still sufficient to support most typical IoT applications. For the conclusion, we proposed a new Slim radio architecture. It throws away most of the power-hungry analog components in order to achieve ultra-low power communication. The power consumption is reduced by around 1,000 times comparing to the commercial-off-the-shelf Wi-Fi device. And we also introduced the asymmetric communication design, which enables Slim radio to directly communicate with the commercial-off-the-shelf Wi-Fi device. No hardware or modifications is needed on the Wi-Fi device side, and all the processing is being done in the software. We also worked with the RFIC research group to tape out the Slim radio IC and verified that the power consumption is as low as 90 microwatts. And the system can achieve a throughput of around 100 kbps at a range of up to 40 meters, which is enough for most of the indoor IoT applications. Similar kind of design can be extended to other techniques such as LTE and 5G, and the asymmetric communication scheme can also be benefits for other kinds of backscattering communication architecture. And that concludes to my presentation, and I would like to take any kind of question. Thank you.